This video accompanies the paper Multi-Camera Trajectory Forecasting with Trajectory Tensors. In our previous work, we introduced the task of multi-camera trajectory forecasting, or MCTF for short. Unlike existing trajectory forecasting approaches, our work is the first to consider forecasting in a network of multiple cameras. In this work, we extend our earlier CVPR workshop paper as follows. We introduce three problem formulations within the MCTF framework. In which camera will an object appear, when will it appear there, and where within the camera view? We propose trajectory tensors, a novel data representation for trajectories which are better suited to the MCTF framework than the traditional approach of representing trajectories as coordinates. Finally, we present a deep encoder-decoder model using our trajectory tensor representation. Our model outperforms several relevant baselines and existing single-camera approaches adapted for MCTF. Firstly, let us introduce the problem formulations. As shown in the video here, we are given a sequence of bounding boxes corresponding to an individual's location as they depart from a camera view. At the first level, we ask, in which camera will the individual reappear? The output is a vector of length k, where k is the number of cameras in the network. The prediction for each camera is a value between 0 and 1, representing the probability that the individual will reappear in this camera view. At the second level, we consider when the individual will reappear in addition to in which camera. The output for this formulation is two-dimensional, with a value for each camera and future time step up to time step m. Finally, we consider where within the camera view the individual will reappear. We divide each camera view into a W by H grid. The output is therefore a tensor of dimension k by m by W by H. A key insight is that the data representation we have defined for the where problem formulation may also be used to represent inputs as well as targets. Trajectories are traditionally represented as a sequence of 2D coordinates. This is a natural representation for a single camera view, but does not generalize well to multiple cameras. How can an object's trajectory be represented as seen from the viewpoint of two or more cameras? To solve this, we propose the trajectory tensor, which is constructed as follows. Consider our set of K cameras. Here a person is visible in cameras 1 and 3. A detector locates the person in each camera view. Detections are turned into heat maps by dividing each frame into a grid. A value of 1 represents an object is present in the grid cell. Heat maps are stacked along the time dimension t and camera dimension k. The result is a trajectory tensor, which represents an object's location through time in multiple viewpoints. The heat maps may be smoothed using a Gaussian kernel along the width, height, and time dimensions, which we find acts as a regularizer. Trajectory tensors are used as either the input to any MCTF formulation or as the target in the where problem formulation. Given a trajectory tensor as input, we propose the following encoder-decoder model, which extracts features using a 3D CNN. These features are then decoded using either a fully connected layer for the which formulation, 1D transposed convolution layers for the when formulation, or 3D transposed convolution layers for the where formulation. In addition to this model, we introduce two more based on a trajectory tensor input representation, and two models based on coordinate trajectories. Please see section 4 of the paper for more details on these 5 models. We also compare with 4 baseline approaches, which are described in the paper. Each approach is trained and evaluated using the WNMF dataset. The dataset is collected indoors using 15 cameras and features 2,000 cross-camera trajectories. More information on the dataset can be found in our workshop paper, where we first introduced WNMF. Here are some examples of our model predicting where an individual will reappear. In this example, an individual is detected in camera 2. After leaving the view of the camera, our model prediction begins. Here are all 15 cameras in the network, each divided into a grid of size 16 by 9. The model, based on trajectory tensor inputs, correctly predicts that the individual will reappear in camera 4, as well as predicting their location for the 12 seconds following the departure from camera 2. Let's take a look at another example. Here the individual departs from camera 13 and reappears on camera 12. Let's take a closer look at the prediction in camera 12. Notice that the prediction is multimodal. That is, the model predicts some chance of the individual continuing straight and appearing on the right side of the frame, and a larger chance of the individual walking down the corridor, as indeed the case in this example. Assigning a likelihood to multiple diverse future scenarios is one of the desirable properties of the trajectory tensor data representation. Results for the three problem formulations are shown here. Our approach, based on a 3D CNN with trajectory tensors, performs the best across the three problem formulations. Explanations of these results can be found in the paper. Thanks for watching. Additional information can be found in the link shown here.